This problem appeared in the 1994 International Mathematical Olympiad, the World Championship of High School Mathematics. It's a puzzle that feels impossible until you find the hidden key. Our mission, together, is to find all positive integer pairs, m and n, that make this fraction a whole number. First, let's state this mathematically. We're looking for pairs of positive integers m and n, for which this expression equals some positive integer, which we'll call k. A quick but important point. If the pair was 1 and 1, our fraction would become 2 divided by 0. Since this is not a positive integer, we can immediately exclude pair 1 and 1. In the language of number theory, this means the denominator, m times n minus 1, must be a divisor of the numerator, n cubed plus 1. This expression looks unbalanced. The n is cubed, while the m is not. Our first goal is to find a way to make the problem symmetric with respect to m and n. If m times n minus 1 divides an expression, it must divide any integer multiple of it. This move is logically sound. Let's see what it accomplishes. We distribute the m cubed, and now we have the term we wanted. Because m times n is congruent to 1 modulo m times n minus 1, it follows that m cubed times n cubed is congruent to 1 cubed, which is just 1. This means that inside our divisibility relation, we can replace the entire m cubed n cubed term with just 1. And just like that, by following the only logical path, we have transformed our expression. We started with the condition that m times n minus 1 divides n cubed plus 1. And we have proven that this forces it to also divide this. Look at that. Just look at that. The problem is perfectly symmetric. If a pair m and n is a solution, then flipping them, n and m, must also be a solution. This changes everything. It's the key to the entire puzzle. We have an infinite number of pairs to check. To make this finite, we can use our newfound symmetry. If we assume, without loss of generality, that m is greater than or equal to n, we can limit our search space. Since the problem is symmetric, we can make a clever decision. Let's just agree to always put the bigger number, m, on the left. So for any pair, we'll assume m is greater than or equal to n. Why? Because we know that for every solution we find, like say, 5, 2, its mirror image, 2, 5, will also be a solution automatically. This simple rule cuts our work in half. It's a beautifully efficient strategy. Let's start with the smallest possible value for n. Plugging in n equals 1, our expression simplifies dramatically. For this to be an integer, m minus 1 must be a positive divisor of 2. So, m minus 1 can only be 1 or 2. If m minus 1 is 1, then m is 2. This gives the pair 2, 1. Our condition m is greater than or equal to n holds true. If m minus 1 is 2, then m is 3. This gives the pair 3, 1, which also satisfies our condition. And remember, because of symmetry, we know 1, 2 and 1, 3 are also solutions. We'll collect all those mirror images at the very end. For now, we just stick to our rule. M is the bigger number. Now let's check the next case. With n equals 2, the expression becomes 9 divided by the quantity 2m minus 1. So 2m minus 1 must be a positive divisor of 9. If 2 minus 1 is 1, then m is 1. But this violates our assumption that m is greater than or equal to n. This is our assumption at work. It prunes the search tree and saves us from checking pairs we'll find later through symmetry. If it's 3, we get m equals 2. The pair 2, 2 is a valid solution. And if it's 9, we get m equals 5. The pair 5, 2 is also a valid solution. Okay, checking cases one by one is fine, but we can't do it forever. How do we prove there aren't solutions hiding out at n equals 1 million? We need an argument that works for all large n. This is the final boss. Because we assumed m is greater than or equal to n, the denominator m times n minus 1 is greater than or equal to n squared minus 1. This gives us an upper bound on k. Using polynomial long division, we can rewrite this bound. Now look closely. For n equals 3 or more, the denominator n squared minus 1 grows much faster than the numerator n plus 1. That fraction is always less than 1. This means k must be less than or equal to n. A very powerful constraint. Now, let's rearrange our original equation. This tells us that n must be a divisor of k plus 1. Let's write this relationship as k plus 1 equals a times n for some positive integer a. We have two facts. K is less than or equal to n, and k equals a times n minus 1. Let's combine them. Substituting for k gives us this simple inequality. Rearranging gives n times the quantity a minus 1 is less than or equal to 1. Think about this. We have two integers. N is 3 or more. A is a positive integer, so a minus 1 must be 0, 1, 2, or more. If a minus 1 were 1, the product would be at least 3, which fails. The only non-negative integer that works is 0. This forces a to be 1, which means for n greater than or equal to 3, k must be exactly n minus 1. This is the key that unlocks the rest of the problem. Let's do a quick sanity check with a known solution. For the pair 5 and 3, n is 3 and k is 2. Our rule says k equals n minus 1. Indeed, 2 equals 3 minus 1. The abstract result holds. Now we substitute this powerful result back into our original equation. Let's rearrange to solve for m. We've already seen this polynomial division. For the left side to be an integer, the right side must be 2. This forces n minus 1 to be a divisor of 2. So n can only be 2 or 3. And here, the entire argument comes together. This whole chain of logic, every inequality, was built on the assumption that n is 3 or bigger. But the result it gives us is that n can only be 2 or 3. The only number on Earth that satisfies both of those conditions at the same time is that n must be 3. The trap closes. Now we plug n equals 3 back in to find m. Solving for m gives us m equals 5. And this gives us our final solution under the m greater than or equal to n assumption. The proof is complete. We've rigorously covered all possible cases. Let's assemble our findings. From our case-by-case analysis, we found these 5 pairs. Now we use our key insight. For every non-equal pair, its reverse must also be a solution. Putting them all together gives us this complete set of 9 pairs. Our hunt is provably finished. So in the end, this was never really a problem about fractions. It was a problem about structure. The key wasn't brute force, but a single, forced move that revealed a hidden symmetry. The next time you face a problem that feels messy and impossible, don't just search for a calculation. Take a step back and look for the hidden structure. Look for the symmetry. Because sometimes, the most elegant answer isn't found by working harder, but by seeing the problem in a completely new light. Thank you for joining me on this incredible mathematical journey. If you enjoyed this proof and want to see more challenging mathematical content, please subscribe to my channel and hit the notification bell. I love exploring the beautiful connections between different areas of mathematics, and I hope you'll continue this journey with me.